In the lecture before, we looked at that these droplets, okay, can actually, what is the mode, how does it actually evaporate. Now, let us look at some of the phenomenology of such a droplet system. Say for example, if you look at this particular plot over here taken from the work of Dsquared et al. Okay, it shows that there is a diameter regression of the droplet due to heating and or combustion. So, basically the droplet diameter shows a decay with time. Okay. Similarly, the droplets which are in a flow field can actually show lot of shape change oscillations, which we are not going to cover. This is called atomization behavior. Okay. So, that means the droplet is a liquid mass, right. So, it is deformable. So, as it deforms, it can form all kinds of strange structures, and these structures might actually atomize in that particular way. These are different modes of atomization. These are called catastrophic breakup. Okay. And there can be situations also where it does not show any such thing and it just shrinks in size. Okay. Just shrinks in size. Okay. So, as you can see over here, this is an ethanol droplet. So, it shows that there is no shrinking, there is just a shrinking in size. So, the droplet just becomes smaller and smaller and smaller. On the other hand, the temperature and the species concentration for binary droplets, especially droplets which has got two components, okay, because of the internal recirculation, they can show very complicated structures, as you can see over here. These are very complicated structures. Forget about this for the time being. This is if you have particulate matter in it, but as a result of the flow, you will get this very nice sophisticated patterns that will start to happen within the droplet. So, it depends on the level of complexity. If you are interested only in this information, this is very easy. Okay. If you are interested more in the deformation mechanism, that is a little bit more difficult. If you are interested what goes on within the droplet, especially if you are interested in what is happening at the droplet scale, your job becomes much more difficult. Okay. So, in order to attack each of these phenomenological events that actually happens, you need a different level of sophistication at each stage. Okay. Say for example, normally we assume that the droplet is spherically symmetric. This is what we told in just the previous lecture when we said that the evaporation flux is the same everywhere. So, the droplet is basically what we call spherically symmetric. That means, everywhere you look around the droplet. So, if this is the droplet and if you go around the droplet, you will find the same evaporation flux, same gasification rate, everything is the same, right. It vaporizes in the same way also. But however, this does not happen when you actually have a flow around the droplet. Now, that flow could be due to natural circulation, it could be due to forced circulation also. You are going to destroy the spherical symmetry that is associated with the evaporation. You are going to destroy that spherical symmetry. Like for example, in this particular case, you can see that the droplet forms like two toroidal cells when the flow around the droplet does not show any separation. That means, for low Reynolds number flow or in the Stokes flow kind of a regime, okay, you will find that this flow field does not show any separation in the aft of the droplet. So, as a result of that, your gas phase streamlines show this nice two vortex structure. Basically, it is a one single toroidal vortex. We are just cutting it across the central plane. So, you are cutting it across the central plane, otherwise it is like a toroid, right. So, that is what you see over here. So, that is the flow field. If the droplet shows any separation, that means the flow shows any separation in the aft of the droplet, you basically get an asymmetry, where is basically you have this 4 vertical lobes. It is basically once again two vortex. One is a toroidal here and the other is a toroidal on the top. So, it is basically segregated into two. So, it destroys the symmetry whenever you have a flow. So, flow destroys the symmetry, okay, inducing what we call recirculation. However, in a spherically symmetric model, we are not really concerned about all those things. So, the most of the droplet models will actually operate on the spherically symmetric principle. Okay. So, droplet vaporization models are of various kinds. One is called the constant droplet temperature model. That means, we take the droplet temperature as constant. One is called the infinite liquid conductivity model. That means, the droplet temperature is uniform, but time varying. Okay. Then there is the spherically symmetric transient droplet heating. This is basically what we call the conduction limit model. That means you take the temperature gradient within the droplet. So, in the first case you basically have a constant temperature, let us call it Td. In the second case you also have the same Td, but this Td can actually now becomes a function of your time. Okay. On the other hand, in the spherically symmetric case, you basically now will have a temperature gradient that will be created at the droplet. Okay. So, there will be a temperature gradient within the droplet. So, there will be a dT dr that will be created. Okay. Then there is something called the effective conductivity model. That means, in this particular model you take the K, the conductivity, and you enhance it. Okay. So, it is this is basically K plus something else, okay, or K multiplied by some factor x. Then there is a vortex model. That means, in this particular model you do take into account the flow field that I showed just the slide before. So, you take into account this particular flow field and you solve for you take this as an ad hoc flow field and then you solve, okay, for the liquid phase and the gas phase transport. And lastly, you have the full solution of the Navier-Stokes equation that will of course give you the most perfect result, but albeit with a very high computational cost, and especially if you are dealing with lots of droplets, this can pose a bit of a problem. So, in increasing order of complexity you basically do this kind of problems. First two are very easy, the third one is basically a little difficult. Okay. The fourth one is variation of the third one. Basically you just improve on the conductivity limit. And then the vortex model basically is somewhere in between an Navier-Stokes equation and no flow situation. That means you incorporate a flow field and try to see the dynamics of that. And the last one is basically the full fledged solution of the Navier-Stokes equation, which is the correct way of doing this thing. So, the first and foremost what we are going to look at is basically look at something what we call the D-square law, right. So, D-square law, this was found by many people including Professor C.K. Law. So, that means if you plot the d by d naught square of the droplet, okay, with time basically, and this time is a normalized time, you will get what we call a straight linear flat drop in the profile, okay, for any type of droplets, because you have normalized it by the initial size. Okay. So, for those droplets you find that of course there is a little spread of the data, but it basically looks rock solid. So, it just decays in that particular way. Now, a D-square law assumes inbuilt there are certain assumptions. Many people use the D-square law in a very ad hoc basis. So, the moment you have something related to droplet you will tend to use the D-square law. So, the D-square law usually uses a spherical symmetry. That means forced and natural convections are neglected. That means it reduces the analysis to basically one dimension, right, because it is spherically symmetric, right. There is no spray effect. That means the droplet is an isolated one in an infinite environment. So, that means if there is another droplet which is so far away that this droplet does not cross talk with the other. Diffusion is the rate controlling. That means the liquid does not move relative to the droplet center, rather the surface regresses into the liquid as the vaporization happens. So, the surface slowly and steadily regresses, but there is no flow that is generated within the liquid. So, therefore, the heat and mass transfer in the liquid only happens because of diffusion with a moving boundary. There is no convection effect. That means the regression is slow and there is no flow that is generated within the droplet. So, there is no question of any convection, as I said. So, it is basically a simple diffusion problem with a moving boundary. It is an isobaric process. So, it is constant pressure. There is a constant gas phase transport properties. That means there is no real change in the specific heats, thermal conductivity, things like that. The last point is very important. This is called the gas phase quasi steadiness. So, there is a significant density disparity between the liquid and the gas, right. It is of the order of 1000. In high pressure it can come down to about 100, right. So, the liquid properties at the droplet surface, that means the regression rate, temperature and species concentration, changes at a rate which is much slower than those of the gas phase transport processes. Okay, so this assumption of course is not valid far away from the droplet, but at the droplet surface, okay, that means the liquid properties change in such a slow rate compared to the vapor phase that we always see what we call a quasi steady kind of a phenomena. Okay. So, that we will see later in the next slide. Okay. So, the gas phase quasi steadiness, and let us prove that using what we call a characteristic time scale analysis. Now, in a standard environment, what we know is that the gas phase heat and mass diffusivities alpha g and delta g, right, let us assume that it is delta g, it can be anything, are of the same order, which is of the order of about 10 to the power of 0 centimeter square per second. But the droplet surface regression rate, if you measure, that means this droplet is actually shrinking, right. So, this rate of this shrinkage is given by k, okay, it is of the order of 10 to the power of minus 3 centimeter square per second. Okay. So, naturally it is 3 orders slower than the corresponding diffusivities, either the mass or the heat. Okay. For a conventional say hydrocarbon droplets, is almost of similar order for other droplets as well. So, thus the ratio, if you just take the ratio of delta g, that is the mass diffusivity divided by this k factor, it basically scales as your rho liquid because of this 3 orders change by the rho gas, correct, because they are also of the order 1000. Okay. So, that means the gas phase mass and heat diffusion occurs much faster than the droplet surface regression. So, the time scale that is involved for the droplet surface regression is much higher than the corresponding time scale that is involved for the diffusion to occur, right. So, we further assume that the properties also vary in the environment also very slowly. So, during the characteristic gas phase diffusion time, the boundary conditions and the locations of the droplet can be almost considered to be constant, because it is happening at a 3 order slower time or slower process than compared to the rapid evaporation. So, the gas phase processes from a droplet perspective can be treated as steady, okay, with boundary variations only occurring at the longer time scales. So, this is the sole reason what is meant by gas phase quasi steadiness. Now, the question that naturally comes, that at what value of this d, okay, this assumption breaks down, that is when the diffusion time is equal to the surface regression time, because this vapor will diffuse, it will continuously diffuse. So, that there will be at some point, okay, where the time that the length scale or some length scale, where the time that it takes for the vapor to diffuse to that length scale should be equal to the surface regression time. So, that is given by, if you just equate the two, and remembering that this is still given as a ratio of the two liquids. So, what happens is that your d infinity by d naught is given by the square root of this. So, therefore, if you calculate d infinity, it becomes 32 d. So, that means 32 diameter apart. If you consider a location, that is the time that it takes for the two time scales to kind of match. So, our distance, our model, that means the D-square model should be valid for distances which are very close. That means we are not considering anything close to 32 diameter, right. So, that gas phase quasi steadiness is one of the most important inbuilt assumptions that is there in the Dsquare law. Okay. So, some more things. Okay. So, if it is a single species, that means I have mentioned fuel because it is for a combustible droplet, but it is not need not be, it can be valid for anything. So, the constant, it is a constant and uniform temperature. So, this is very important. So, the droplet temperature is constant and uniform. So, I mean, where does all the heat go? If you ask the question, all the heat basically goes towards evaporation. So, that is what happens. Okay. So, therefore, where does so the combining with this particular thing, we see that the liquid phase heat and mass transport processes are completely neglected, because you are assuming it is a constant temperature, right. It is a constant temperature, there is no convection within the liquid droplet. So, therefore, where would all this heat and mass go? It just goes towards vaporizing. So, you basically have a very simple equation, and we will show that equation, where you just take into account this particular physics, that you are not solving anything basically within the liquid phase. So, that is the beauty of the D-squared model, is basically, as we can call it, is basically essentially a gas phase model, right. And then the ninth assumption, so there are 10. So, the ninth assumption is basically the saturation vapor pressure at the droplet surface. Now, this is based on the assumption that the phase change occurs at a rate which is much faster than the gas phase transport. So, therefore, the evaporation at the surface is at the thermodynamic equilibrium state, not really valid if you are dealing with extremely rarefied flow and things like that. Okay. There you can actually have this recoil pressures and things like that. So, what happens is that we always assume that compared to the gas phase now, this vapor that exists at the liquid vapor interface, which you already showed exists at the saturation temperature, exists as a saturation, that is the saturation pressure. So, that particular phase is always there. So, it is in a thermodynamic equilibrium state. Okay. So, basically evaporation happens from the liquid to the gas across the interface. It is like I am jumping from the liquid to the gas phase, and in the gas phase I am existing at the saturation pressure of whatever is the surface temperature, right. Okay. So, so that is what it is, and it occurs at a rate which is much faster than the gas phase transport. Now, Soret, no Soret effect or Dufour effects are basically, and radiation effects are basically admissible over here. Now, Soret and Dufour, these are basically second order effects. Okay. You know that your thermocouple is basically operates on these kind of things, the second order effects. So, Soret means that there is mass flow because of temperature gradient, and Dufour means there is heat flow due to concentration gradient, right. So, these effects are basically neglected at this particular point, and also if the droplet is not too hot, okay, the radiation effects can also be neglected, though this is not always the case. Okay. This is not always the case, it is a very situation dependent problem. Okay. So, let us look at the heat and the mass transport of the droplet in a slightly in some block diagrams, because we have described a few things. So, let us first write the evaporation of the droplet. So, what happens during the evaporation of the droplet? The surface temperature is constant, which is also the saturation temperature. So, what we see over here is that if we allow also this surface temperature to change with time, that may or may not be true, it depends, okay, but you can take it to be constant also. So, whatever heat that is being supplied, this Q dot, is either going towards the latent heat and towards the sensible enthalpy, correct. So, latent heat means that it is basically going towards the evaporation. So, this m dot is basically the mass that is getting evaporated, and HL that you see is basically the latent heat of vaporization. So, Q dot is basically the heat that is being supplied to the droplet from whatever means, right. So, there is some heat supply that has to happen, right. The term on the right hand side that you see is basically takes into account the variation of the droplet temperature. Okay, it is m Cp into the dt by dt. So, that takes into account if the surface temperature is constant, but essentially it can vary with time. Now, in many of the cases that may not be the case also, you can just supply the heat and it goes totally towards evaporating the droplet. Okay. Now, m dot, which is given by basically dm by dt, that means the rate of evaporation of the droplet, is given by this particular form, where as you can see that this particular term is basically the evaporative flux, and S is basically the surface area. So, S is the surface area, this is basically the evaporative flux, all right. Now, the evaporative flux of the droplet now can be written in terms of the concentration gradient, either this or this. This is basically written in terms of mass fraction. This is nothing but the Fick's law. Fick's law is the same as what we have in the case of your thermal conduction also, or the thermal diffusion also. Okay. So, the Fick's law is the law that we fall back on, okay, when there is a diffusion problem involved. So, in this particular case it is a concentration gradient that is creating it. It is the rate of change of the, it is the change or the spatial gradient of the concentration with the distance, right. Now this can be also written as in a simpler form, if you assume that it is almost like a linear variation, which in most of the cases will be true. This is basically the diffusivity, the mass diffusivity, and this is basically the surface concentration minus the far field concentration divided by some parameter which is d, which is usually taken as one droplet diameter away, right. So the same thing now can be written in terms of a composite way, which is basically given as this particular expression, where you can see two terms. One is a Sherwood number. The Sherwood number is basically the Nusselt number for mass transfer. So this is basically nothing but is like the same as the Nusselt number, except that it pertains to mass transfer and not heat transfer. And then you have the d, which is the diffuse, this is the diameter, this is the diffusivity, these are the corresponding difference in the concentration gradients. Now in order to, so you can see from this equation you need basically two terms, right. One is this term and one is this term. For this term HL is already known, right, because it is a latent heat, it is known, and it is a constant temperature. So you know exactly what the latent heat that you need. M dot is something that we need to find out, and Q dot is something that we need to find out, right. So M dot and Q dot. So already M dot we found out using this. So there is of course a term like Sherwood number. Now this Sherwood number can be written in terms of Reynolds number and Schmidt number, where the Reynolds number is nothing but the difference in the velocity scale, if there is a velocity between the gas and the liquid. If there is no velocity, which is the case in the case of a spherically symmetric droplet, as in the case of your Dsquare law, this particular term will basically vanish. So it will be given in terms of only 2, okay. So, but this is also called the Rans-Marshall correlation, very popular correlation in the droplet literature. So the Reynolds number is basically given as the relative velocity between the two, okay, between the droplet and the ambient. So you can see that it actually enhances the mass transfer, which is kind of obvious. We told you earlier that the J, this SH is basically like a flux term. So it basically represents a flux term, so therefore it gets enhanced. The convective heat transfer process can be written as, therefore, Q dot is equal to this. On the other side, the Q dot which we need is basically written as Kc pi d square Tc minus Td, okay, divided by d, okay, where the Nusselt number is also written in a very similar form, once again in terms of Reynolds number and Prandtl number. As we know, the heat transfer will also get enhanced if there is a flow. So if there is no Reynolds number, once again this goes down, you are left with only 2. So now that you have got Q dot and you have got M dot, you can solve this equation and you can evolve that what will be the surface temperature of the droplet to begin with time, right. Okay, and you can also calculate that what will be that. But if in the case that you do not require at all the temperature change, if this is constant, you can just substitute dm by dt as 4/3 pi r cube dt by dt of that, and you can find out what will be the diameter regression, and that is exactly what the Dsquared law actually does. Okay. But this is to give you a bird's eye view that how these problems are solved. Basically you solve for Q, you solve for M dot, and then you combine the two and you solve the equation. Okay. So the Dsquared law, going very fast. So we, from the continuity you already showed that these are the, as I say, Dsquared law is only about the gas phase, there is almost nothing that is solved on the liquid phase. So you can go through the motion of this, okay. There are a bit of complications which I really don't, you don't have to really go through it in that kind of a detail, because I have already said what are the key things. Okay, it is physically reasonable because the phenomena of interest is a spherically symmetric diffusion control process. That is exactly what we are looking at over here. So all that people need to do is to solve for the equations in the vapor phase. That is all that is required, right. And here you see that some of these terms that you see over here, these are called the heat and the mass transfer numbers. Again, not going into the details of all these things, okay. Ultimately let us focus on the answer that the regression of the droplet diameter is given in terms of the initial diameter and some factor k, which is called the surface regression rate, which is constant. So, this basically if you plot it, you will get a curve which is basically RS square by RSO square, okay, which where the slope of this curve will be given by kV. Okay, and kV is basically the slope is basically given as an expression like this, where this is called the Spalding heat transfer number. This BHV is basically given here. It's Cp T infinity minus Ts, which once again is the infinite temperature minus the droplet surface temperature, and QV is basically whatever heat that is actually supplied to the droplet. It has got a very similar form as what we saw earlier. So, this is the surface regression rate that you can solve, and you will find that it actually scales linearly with the square of the droplet diameter. So, therefore, this is the D-square law, which takes into account that only the gas phase and no liquid phase equation is at all solved. If you however are doing model 3, which is basically this one, the spherically symmetric transient droplet heating. That means in that particular case, unlike the D-square law, you have to solve for the liquid phase. For the liquid phase equation that you are solving is basically nothing but what we call a simple transient heat conduction equation. Okay. So, it does not consider any flow, and the temperature field is conduction driven within the liquid. So, all you need to do is at the boundary you need to match the temperature slope at the boundary and the symmetry condition at the droplet center, because at the droplet center the temperature gradient should actually go to 0. This is because you have basically it is a symmetric droplet, right. So, all you need to do is solve this extra piece of equation, and you need to adjust the boundary condition accordingly. Do not bother about these terms so much, because these are basically a little bit more complicated. All you need to do is match at the droplet gas interface. Okay. So, this is for example some of the temperature profiles that you get when you actually solve the spherically symmetric problem. So, you can see it comes like this, and you can see the slope goes 0 over here, because it will go like that on the other side of the interface. Okay. So, this was the work done by Professor Shiriniano. If you compare the 4 models, that is the quasi-steady, rapid mixing, the diffusion limit, and the D-squared law, you find that in the R squared scale all of them kind of show more or less similar stuff. That is why your D-squared law is a very good assumption to begin with, if you just are interested in knowing the decay of the droplet diameter. But if you are interested in something more than that, then it becomes a little bit of a problem. And lastly, if you want to solve for the vortex method, then there is this spherical vortex that you have to solve within the droplet along with the free stream, and you have to take into account not only just the liquid conduction equation, but you have to write the full Navier-Stokes equation in the liquid phase. If you assume the velocity profile, then you can just do away with just the energy equation in the liquid phase. Okay. So, this is more complicated, and you are strongly recommended to look at the other course on this, where it is covered in much more details. Okay, and how is it exactly covered, all those things are there mentioned. So, with this particular thing, we basically come to the end of this convective heat transfer course. So, what we have done is basically just a small recap. We have basically studied the entire spectrum of canonical convection problem. We emphasized more on the scaling argument, we emphasized more on the analytical solutions and the integral solutions, and once those integral solutions have evolved, we have started to look at some of the interesting insightful discussions related to those problems, which has given us a lot of insights into forced convection as well as natural convection as well as turbulence, and as well as now a little bit on the multiphase systems. Okay. So, we have covered basically forced and natural convection for laminar flows in details. Turbulence flow, we just gave you some insights of what happens in the turbulence flow, and of course, we did a little bit on what we call the multi-phase systems in just a couple of lectures to just give you a brief overview of what happens. We also did a lecture on the diagnostic techniques, especially TLC and IR thermography, just to give an idea that all these things that we say, that we have measured heat transfer coefficient, we have measured the mass transfer coefficient, we have measured the surface temperature, how these things can be done, okay, experimentally, because you need experimental validation for everything. So that was done using these kind of analogies, okay, this kind of tools, not analogies. So we did that in quite a bit of details, and there were some homework problems that we also solved, just to give you an idea that how to solve attack typical problems in this particular area. But the main takeaway points for this particular work, from this particular course, is basically you have to look into details that what are the key factors, right? What are the key factors that affects convective heat transfer? So you have to have an insight about fluid dynamics, you have to have an insight in heat transfer, and you have to have some insights in how these equations are coupled, okay, how they actually go from one stage to the other, okay, and what are the different scales that are relevant, concepts like boundary layer, concepts like fully developed profile, what does it mean in terms of temperature, etc. So I think if you study all these things in details and follow the lectures, you should have a very clear idea of what convective heat transfer is. This is the first course, so nothing advanced, okay. So you can have a reasonably good idea of what it is before you move into more advanced systems, especially involving multi-phase. So we end the course here, and wish you guys all best of luck.